In this video, I was planning on going over the example problems for exam 2, and so I'll just go through those. So the first problem says the irreversible liquid phase acid catalyzed isomerization reaction, and then it gives you this reaction. So you have A plus sulfuric acid to C plus sulfuric acid. And so it says it's irreversible. It says it's liquid. It's carried out isothermally, so isothermal. It's a semi-batch. And then it says 4 mole liter solution of sulfuric acid is fed at a constant rate of 4 liters per minute. So we know that V naught is equal to 4 liters per minute, and that has a 4 mole liter solution. So V naught is equal to 4 liters per minute of H2SO4, and then C B naught is equal to 4 moles per liter. And I'm going to rename H2, I'm going to rename sulfuric acid B, just to make this easier. And then it says the initial volume of, so you have an initial volume of pure A in the reactor of 200 liters, so V initial is 200 liters. The concentration of pure A is 10 moles per liter, so C A naught is equal to 10 moles per liter. The reaction is first order in A, so first order in A and first order in B, first order in A and B. And let's see, and then it gives you the specific reaction rate. So K is equal to 0.05 liters per mole per minute. The catalyst, so it says the catalyst is sulfuric acid, so B. It says that it's not consumed during the reaction. So from that we know that CB is equal to CB naught. And then it says derive a relationship that relates the conversion of A to the known system parameters and determine the conversion of A after 25 minutes. And then it wants to know how much C is formed after that. So first of all, we can draw a picture of what's happening. So you have a semi-batch reactor. It starts out with pure A, and we add B. So we're adding sulfuric acid, and the reaction actually looks something like this. Since sulfuric acid is the catalyst. So to solve these problems, this is still the same as the other problems we've been doing. So the very first thing you want to do is start with a mole balance. So start over here. And the other thing with this, it says derive a relationship that relates x of A, so the conversion of A, to known system parameters. And so since it's asking for the relation to conversion, we know that we need to use a mole balance that has conversion in it instead of the concentrations. And so the mole balance we want to use is this one. And this is, so Na naught dx dt is equal to minus RAV. And this is on table S2-1 in the text for a batch reactor. And so then the next thing we need is a rate law. And so it says it's first order in A and B. So we know that the rate is equal to K A, and actually just called that K, so K C A C B. And I'm going to erase some stuff real quick and then do the stoichiometry. We need an equation for CA and CB, so get that from the stoichiometry. So we know that CA is equal to NA over V, and we know that NA is equal to NA naught 1 minus X, and we know that since this is a semi-batch reactor, the volume is actually changing. So V is equal to the initial volume plus the volumetric flow rate multiplied by time. And then CB is the same thing. It's equal to NB over V. And so this is where things kind of get a little bit different with the semi-batch, because we're adding B. So we have NB initial plus, and then we have FB naught multiplied by time minus what was there initially, and then we have the same thing for volume, so just V naught plus V naught T. And so in this case, and this equation was from, this is equation 4-65 in case you want to go look at it just to kind of see where this came from. But basically you have your, oh, this is Na naught X. So you have what was there initially, and in this case that's actually 0 because there wasn't initially any B in the reactor. And then you have, this is your volumetric flow rate multiplied by time, so this ends up being how, so if you look at the units for this, you have F, so F B naught, and the units are moles per time. So then if you multiply this by a time, you just get total moles. So this ends up being the total amount of moles that were of B that were added during this time. And then this is the amount that reacted. So in this case, we also know that this is 0 because it's not being consumed in the reaction, like it gives us that in the problem. So in fact, just look at the exact wording. The catalyst is not consumed during the reaction. So then we have CB is equal to F B naught T over V naught plus V naught T. And then it would be better to have this in terms of CB naught, so we can rewrite that as C B naught V naught T over V naught plus V naught T. So then we can just combine everything. I'm going to erase some stuff real quick. So then combining these equations into the mole balance, so we combine the stoichiometry into the rate law and then into the mole balance. And with these problems, if it tells you, just do what it says. Like if it's a problem that can be solved by hand, then it'll probably tell you, like in this case it says derive a relationship. If it's something that needs to be solved numerically, then and it's on the exam, then it'll tell you write down the equations that you would put in your solver. And so then you would just go through and write like the equations you would put in. And so you might combine a few things, you might not. Just be really specific about what equations you're putting in, and then make sure you list all your constants. So if you have all your equations that you're putting in the solver, and then just be really clear, like, okay, this is what I'm putting in for CB naught, B naught, CA naught, etc. Okay, so combining these, we have NA naught dx dt is equal to, and then we have the rate, so K A, I keep forgetting that I'm just calling that K and not KA. So K, and then I had NA naught 1 minus X over V naught plus V naught T, and that was multiplied by CB naught V naught T over V naught plus V naught T. And then if you remember, there was also, this was the mole balance was NA naught dx dt is equal to the rate multiplied by the volume. And so then the volume, since we know it's changing, it's V naught plus V naught T. And just make sure you put this equation in for volume and not just write V there. So then this cancels, and this cancels. And we just end up with an equation that looks like this. dx dt is equal to K 1 minus X over V naught plus V naught T CB naught V naught T. And when you're writing this volume versus a volumetric flow rate, just be really careful to write them different. Like, just be really careful, because I mean, they look the same. So just make sure that you write those so you can distinguish them. And so then we can separate and integrate. And so if we do that, we get 0 to x, 1 over 1 minus x dx is equal to, and then in this case it's 0 to time, but it told us the time was 25 minutes, so we can just plug that right into the limit. And then we have K CB naught B naught T over V naught plus V naught T dt. So then coming over here, we know that this integration, so if we integrate this, we know that that is equal to minus natural log 1 minus x. And this is kind of what I was talking about earlier with the integration stuff, where it's easy to just write that and you don't add in c and you don't apply the limits, because if you were to add in c, you would get so if you apply the limits 0 to x, then you get minus natural log 1 minus x minus natural. So natural log of 1. We know that this is 0. So this is why it can be easy to kind of skip this step, because you're just like, oh, well, it's just 0. But if you messed up yeah, I would just be really careful about this. So minus ln 1 minus x, and then that is equal to, and then he actually gave you the integration for an equation that looks like this, and that was t, so t over v naught minus v naught over v naught squared, natural log v naught plus v naught t and then this is all multiplied by Ka. I'm just going to write this over here, so just plug that in there. So Ka Cb naught v naught, and then if you apply the limits, this is from 0 to 25. I'm just going to erase some stuff real quick. So then we can actually divide, well, we can divide this through, so then that goes away. And so then we end up with minus natural log 1 minus x is equal to, I'm going to actually write these in this time, so K Cb naught, and once again this is K, I don't know why I keep writing Ka, and then T minus V naught over V naught, natural log V naught plus V naught T, and then 0 to 25. Then if we go in and apply the limits, then you get minus ln 1 minus x is equal to K Cb naught, and the first one's 25, so this would be 25 minus V naught over V naught, natural log V naught plus V naught multiplied by 25 minus zero, because it's 0 this time, minus V naught over V naught, natural log V naught plus 0. From here, we're solving for x because we want to find out how much conversion of x, or how much conversion of a have we had in 25 minutes. So from here, we can just start plugging in all of our constants. So we know K, we know Cb naught, we know V naught, and we know the initial volume, we know the volumetric flow rate. And so we should just be able to plug in all of these numbers and kind of simplify this down into something that we can solve for x. And I'm not going to go through and plug all those numbers in this video, but if you do that, you should end up with minus ln 1 minus x is equal to 0.94. So then if you solve for x, you get x is equal to 0.61. So you know that there's been 61% conversion of A in 25 minutes. So then it says, so determine the conversion of A after 25 minutes, and then how much C is formed. So to calculate C, we know that, I'm going to erase this real quick. Going back to stoichiometry, we know that C is equal to n A naught x is equal to C A naught V naught, and this is the volume, not the volumetric flow rate, X. And so then we know that that's equal to, we know that Ca naught is 10 moles per liter. V naught is 200 liters, so 200 multiplied by X, which was 0.61. And so then that was, so then the number of moles of C was 20 moles. Number 2, it says you have a second order reaction, so second order, that it's 2A to product. And it's in a PFR. The initial concentration is 2 moles per liter, so Ca naught is equal to 2 moles per liter. The reactor volume is 500 liters, so V is equal to 500. And the volumetric flow rate is 250 liters per minute, so V naught is equal to 250 liters per minute. And then it says a single pass conversion of 50% is obtained, so X equals 0.5. And then it says, for operational purposes, it is decided to recycle part of the exit stream to increase conversion. The reactor 10 times the size of the original was used, and the target conversion was 80%. What recycle ratio is required to achieve the target conversion? So this is reactor 1. And then it says that for the second reactor, so we have a recycle reactor, so, and that the volume of it is 10 times the original volume, so 10 times 500. And the X is equal to 0.8, and it's asking for R. So I'm just going to write that this one's the recycle reactor. So for this problem, you can really get into a lot of equations for recycle reactors and for this problem. And if this were on homework, I would be like, okay, I would tell you to go through and derive the equation for a second order recycle reactor and write things down just so everything's clear and you know that you know what you're doing. But on the exam, if it tells you you have a first order recycle reactor or a second order recycle reactor, you've already derived the equations for those in homework 5, I believe it was. Yeah. And I also did a video on recycle reactors, so I'm not going to go through any of the derivation stuff in this video because it would be way too long. So if you want to really review recycle reactors, go back and watch that video I made on recycle reactors. And you can also Google recycle reactor, and the author of our textbook, Vogler, has a bunch of information on his webpage about them, so you can look at that too. But all I'm getting at with this is, if you get something like this on the exam and it says, okay, you have a second order recycle reactor and you want to calculate R, or you want to calculate conversion or volume or something else, then you probably want to go straight to the integrated form of the equation without going through and deriving it. I'm gonna derive it in this video, but I'm just showing you on the exam what you probably want to start with. So it says second order recycle reactor, so that is K tau Ca naught over R plus 1 is equal to Ca naught multiplied by Ca naught minus CAF over CAF CA naught plus R CAF. And so this is the second order recycle reactor, and this assumes no volume change, so V is equal to V naught. And you can kind of see where you can go from here. You want to calculate R for X is equal to 0.8. So you would plug in there's an equation that relates so this is your final concentration. So we know that X naught, and I'm going to go into this in more detail in a minute. I'm just giving you the method real quick. So X naught is equal to CA naught minus CAF over CA naught. So then you can solve this for CAF, plug it in here, and then you know that X is 0.8, and the only thing you don't know in order to solve this is K tau, and you can get that from your PFR. So you would solve the PFR equation, solve the mole balance for the PFR, and get K tau, and then you can plug that into, actually, you're not solving for tau, you're only solving for K, because you know you can calculate tau. So yeah, you solve the PFR for K, and then plug that into here, and then you can solve, you should have everything you need to solve that equation for R. And I'm just going to go through this. The reason why I wanted to kind of point that out is because on the exam, some of the stuff I'm going to go through for this problem, you don't want to be going through and deriving this stuff on the exam. But I think it's important to see like where this equation came from and how to do it, especially with a recycle reactor, because you can work with your equations in a few different ways. And so, and then so on the exam, if he says to derive something, like I have no idea, he might ask you to derive a mole balance, or derive the integrated form of your equation for a recycle reactor. Like, I have no idea if he's going to ask that or not, but I just feel like you should know how to do this, even though on the exam, if he had a problem like this, you would just want to skip straight to this equation. So anyway, so just starting at the beginning, you approach this problem the same way as all the others. So first of all, you do a mole balance. And so this is where things can get a little bit tricky. You can do your mole balance two different ways for a recycle reactor. So you can either have V is equal to FA1 0 to XS, and I'll draw this in a minute so I can show you where all this is, dx over your rate, or you can have V is equal to FA naught 1 plus R X naught R over R plus 1 X naught D XA over minus RA. So if I just draw a recycle reactor real quick, you have some stream coming in, some stream coming out, and then you have a stream coming off that goes back in. So this is your recycle. And then say you have FA naught flowing in, FA1 would be right here. So FA1 is, and this is your recycle stream, so FA1 is FA naught plus your recycle stream. And then you have a stream over here, say that's FA2 coming out of the reactor, and then FA3 is And actually, just to stay with his nomenclature, I'll probably call this FA final. So FAF, because he has like CA final. And so, yeah. So FAF, so then this FA2 is equal to FAF plus FAR. And then if you remember R, which is the recycle parameter, is equal to FAR, is equal to the ratio of the recycle stream to this final stream coming out, so the FAF. And that applies, that should be the same for all species, so you could have F, so this is equal to FIR over FIF. So just so you understand what the definition of R is. And then you can have two different, you can calculate a few different conversions in this reactor. First of all, you can have X naught, which is the overall conversion, or you can have XS, which is the conversion per pass. So if I just write those down real quick, just so that you understand these. So X naught is equal to F A naught minus F A final over F A naught, and XS is equal to F A1, so right here, minus F A2, so right here, divided by F A1. So for XS, we're looking from here to here, and for X naught, we're looking at the entire thing. Okay, so you have your mole balance. Now you need the rate law, so write that down. So minus RA is equal to K CA squared. And we know this because it said the second order. And so then we can write the stoichiometry. So I'm going to erase this real quick. Stoichiometry, and then this is where you need to be careful, because depending on which mole balance you're using, you have a different equation for concentration. So for this first one, if you're using this form of the equation, then this would be CA is equal to CA naught 1 plus R 1 minus X naught over 1 minus X 1 plus R. And if you're using this form of the equation, then CA is equal to C A naught 1 minus X A. So this one goes with that. This one goes with this one. And I derived this equation in the recycle reactor video, so go back and look at that if you're unsure how this was derived. And so then you can combine these, and if you go through the math, you'll find that you end up with the exact same answer for either. And so I might just go through. I'm going to do both, but it turns out if you use this one, the math is simpler. So that might be one benefit for using this one. So I'm going to erase some stuff. Starting with the first equation, you have V is equal to FA1 0 to XS dx over minus RA. And so then if you combine everything and plug it into this, and we can also plug in an equation for FA1. So FA1 is equal to CA naught V naught 1 plus R 1 minus X naught. And this is something I derived in the recycle reactor video. So then plugging in our rate and everything else, we have V is equal to CA naught V naught 0 to XS dx over K CA naught squared 1 plus R 1 minus X naught one minus X over 1 plus R squared. So then that goes away. And coming up here, so I just want to kind of rearrange some things. So I have C A naught V over V naught K is equal to 0 to XS 1 plus R squared over 1 plus R 1 minus X naught 1 minus X squared. And this is dx. Just rearranging this again, you can get C A naught. I'm just going to rewrite this as tau. So TA naught tau K is equal to 1 plus R squared over 1 plus R 1 minus X naught 0 to XS dx over 1 minus X squared. You can integrate this, and being really careful to apply the limits like I talked about before, then we get CA naught tau K is equal to 1 plus R squared over 1 plus R 1 minus X naught 1 over 1 minus XS minus 1. So then at this point we need a relationship that relates XS to X naught. And I can't remember if this was something that was derived in homework 5. I'm just going to erase some stuff real quick, and then I'll show you how you can get this equation in terms of X. So we want a relationship between X naught and XS. So we know that FA is equal to FA1 1 minus XS, and that's equal to FA naught 1 plus R 1 minus X naught. And then we know that FA1, so FA1 is equal to FA naught 1 plus R 1 minus X naught. So then we can get an equation with XS as something with XS is equal to something with X naught. So this is FA naught 1 plus R 1 minus X naught 1 minus XS is equal to FA naught 1 plus R 1 minus X naught. So then these cancel. Then I'm not going to work through all this math in detail, but if you go through and solve this for XS, what you get is XS is equal to X naught over 1 plus R 1 minus X naught. And so then what you can do is plug this equation for XS into here. And so then you can write this in terms of X naught. So I'll do that real quick. And I think I went through this in the Recycle Reactor video in detail, so that you can go look at that. But if you just work through all this math, you'll get this. So what I want to do is I'm just going to write down this equation for xs is equal to x naught over 1 plus r 1 minus x naught. So then if I plug that into here, I get c a naught tau k is equal to 1 plus r squared over 1 plus r 1 minus x naught over 1 minus x naught 1 plus r 1 minus x naught, and then this is all minus 1. And then so you could use this equation in this form, or if you want to write it in terms of concentrations, so if you want to get this, well, basically take this equation and put it in this form. What you need to do is solve this equation for CAF, or actually, sorry, take that back. You can just plug this x naught into here, and so then you get this equation in terms of CA naught and CF. So if I do that, I get C A naught tau k is equal to 1 plus r squared over 1 plus r 1 minus, and I'm plugging in this equation for x naught, so that's C A naught minus C A F over C A naught, and that is multiplied by 1 over 1 minus, and then plug this equation in for x naught again, so C A naught minus C A F over C A naught, and that is divided by 1 plus r 1 minus, and then this again, so C A naught minus C A F over C A naught, and this is all minus 1. Sorry, I kind of scrunched that. And then if you go through the math on this, you end up with this equation. And so that might be something you want to do just to prove this to yourself, but you end up with this, and so you can kind of see why if there's a reason to use this equation on the exam, you probably don't want to go through this whole derivation, but I still think it's important to know how it's done. And so now I want to, so this was the derivation using this first mole balance, so the V is equal to FA1 0 to XS dx over minus RA. And so now I want to go through and redo this derivation using the second mole balance. So I'm just going to erase this stuff real quick. The mole balance was V is equal to FA naught 1 plus R x naught R over R plus 1 x naught d xa over minus RA. The rate is still the same as second order, so minus RA k CA squared. And then for the stoichiometry, you had CA is equal to CA naught 1 minus XA. So then you can go ahead and combine some of this stuff, and using FA naught is equal to CA naught V naught, we have V is equal to CA naught V naught 1 plus r x naught. This is r plus 1 x naught d xa over, and then we can put in the rates. So k ca naught squared 1 minus xa squared. So then that cancels. And we have, and I'm going to divide the v naught over and multiply the k over. So then I have tau k, and I'm going to also divide the, or multiply the ca naught over. So I have tau k ca naught equals 1 plus r x naught r over r plus 1 x naught d xa over 1 minus xa squared. So then if I integrate this, I get, and divide the 1 plus r over, I get tau k ca naught over 1 plus r, and that is equal to 1 over 1 minus x naught minus 1 over 1 minus r over r plus 1 x naught. So then we can go back to this equation that we had for x naught, and I erased it, so I'll write it again. So x naught was equal to ca naught minus caf over ca naught. So then we can plug this in for x naught. Now let's erase some stuff real quick. So then we get tau k ca naught over 1 plus r is equal to 1 over 1 minus ca naught minus caf over ca naught minus 1 over 1 minus r plus 1 multiplied by ca naught minus caf over ca naught. And then if you go through and simplify this, you end up with this again. So this is, so you end up with the same answer both times. So anyway, just coming back to this, if you have a recycle reactor problem on the exam, unless it specifically tells you to derive this equation, I would not go through all this math on the exam. I would just jump straight to this equation. So anyway, but I wanted to show you how that derivation is done. You should know how to get the second order recycle reactor equation. So I'm going to erase some stuff. And coming back to the actual problem, the problem 2 of this exam review, you were given this information and you said, okay, I have a second order recycle reactor, so you wrote down the integrated equation for that. And we're looking for r, so we know tau, because we know v over v naught. We can calculate CAF, so we know that CAF is equal to ca naught 1 minus x, and we know that x is 0.8 in this case, so then this is just equal to ca naught, which is 2, multiplied by 1 minus 0.8, so that's 0.4. And we know ca naught, and so the only thing we need is k, and we can get that from the PFR. So we need k, get from PFR. So then we can just go through, and we just go through the regular routes. So we know mole balance, V is equal to FA naught 0 to x dx over minus RA, and the rate, So minus Ra is equal to K Ca squared. And stoichiometry is just Ca is equal to Ca naught 1 minus x. So then if we combine everything and integrate, we get that Ca naught tau k is equal to 1 over 1 minus x minus 1. So then we know Ca naught, I'm pretty sure we know Ca naught, we know tau, and we know x. So Ca naught, so we know 2, and then tau is v over v naught, so that's equal to 500 over 250, so that's 2k is equal to 1 over 1 minus 0.5 minus 1, so k is equal to 0.25. And then just real quick, I just wanted to show that you could have also gotten this from using the mole balance for concentration. So just going back to the mole balance, you could have also said V is equal to V naught CAF Ca naught dCA over minus Ra. And then using the exact same stuff, so the rate, and then we don't actually need this because we're integrating with respect to Ca. So I'll just plug the rate directly in, so K Ca squared. So then if you integrate this, you end up with V over V naught multiplied by K is equal to 1 over Ca minus 1 over Ca naught. So this is equal to Ca naught minus Ca over Ca naught Ca. And then if you plug everything in again, so you have 2 for tau k is equal to Ca naught is 2. We can calculate Ca because we know Ca naught and we know x is 0.5. And if we do that, it ends up being 1. 2 multiplied by 1. So then if you solve for k, you get that k is 0.25. So same thing. So I just wanted to point out that you could have gone either route and gotten the same answer. So for this problem, it probably doesn't matter which route you pick, but in general, if you're looking for a conversion, or say it's asking for a conversion, then you'd probably want to use this. Or if it's asking about concentration, then you probably want to use this one. Going back to the recycle reactor, we have K, which is 0.25 multiplied by tau. And so tau is different for the recycle reactor because you have a different volume. So your volume is multiplied by 10. So tau in this case ends up being 20 instead of 2. And then you have Ca naught, which is 2, over R plus 1. And that's equal to Ca naught, which is 2, multiplied by Ca naught again, minus Ca final. And we can get Ca final because we know that Ca is equal to Ca naught 1 minus x. So if we plug in 0.8, then we get CAF as 0.4 over CAF Ca naught, which is 2, plus 0.4 R. So then you can solve this equation for R. And if you do that, you get that R is equal to 3. So for number 3, it says the following reaction is taking place in a PBR. So you have a packed bed reactor, and you have this reaction. You have 2A plus B to 2C. And then it says the reaction rate is given by, so it gives you the rate. Ra prime is equal to K Pa to the 2/3 Pb to the 1/3. And then it gives you K is equal to 30, and that's mole ATM per kilogram of catalyst per hour. And then it says A and B are fed in stoichiometric proportions, so A are fed in stoichiometric proportions, and that T is equal to 227 degrees C, P is equal to 5 atmospheres, and that the feed mixture contains 80% inerts, so 80% inert. And the feed rate of A is 500 moles per hour, so F A naught equals 500 moles per hour. The pressure drop parameter alpha is 0.03 kilogram minus 1. So then it says derive an expression that relates the weight of the catalyst to the conversion in the reactor. So we're looking for so basically we're looking to set up the mole balance and then solve it. And then it says find the weight of the catalyst necessary to achieve 20% conversion. So what is the weight when X is equal to 0.2? And then it says assume epsilon x is much smaller than 1. So then we just start working through this problem like all the others. So first of all, we want to do a mole balance. And it's a PBR, and we have a pressure drop, so we need to write the differential form of the mole balance equation because we have a pressure drop. So FA naught dx dw is equal to minus RA prime. Then we can write the rate law, which the rate law was already given, but I want to rewrite it so that the PA and PB are in terms of concentration. So minus RA prime is equal to K PA to the 2/3 PB to the 1/3. And this is equal to K CA 2/3 CB 1/3 RT. And that's because CA is equal to PA over RT. So then I can do the stoichiometry. So I need to write an equation for CA and CB. So CA is equal to CA naught 1 minus x over 1 plus epsilon x multiplied by y, because remember we have a pressure drop, so y is this, so this is P over P naught. And we have CB is equal to CA naught theta B minus B over A x over 1 plus epsilon x y. And then theta B, if you remember, that's FB naught over FA naught. And it already told us these were fed in stoichiometric proportions, so we know that FB, this would be 1 to 2, so that's equal to 1/2. And then this b over a, we have 1 over 2, so this b over a is also equal to 1/2. So, and I'm not going to rewrite that, but, and then this, so since I'm assuming that epsilon x is really small, I could theoretically just set that to 0 right now, but I'm going to leave it in this form just so it's a more general equation. So then we need to write the equation for the pressure drop, and that is dy dw is equal to minus alpha over 2y 1 plus epsilon x. And so this is assuming isothermal. So then this is really where we need this assumption, because right now we have two coupled ODEs and we want to get an analytical solution, so we need to figure out a way to solve this, and so we can plug it back into this equation and solve it. So by assuming that epsilon x is really small, we can just say that that's 0. And then if you remember, if we do that, then we can integrate this and we get y is equal to 1 minus alpha w to the 1/2. We can start combining things so we can solve this, and I want to start with the rate law, so I'm going to plug that into there and that into there. So if I do that, I get minus RA prime is equal to K CA naught 1 minus x over 1 plus epsilon x y to the 2/3 C A naught 1/2 minus 1/2 x over 1 plus epsilon x y to the 1/3, and this is multiplied by RT. I can pull out the CA naught, I'll just show you the math. So RA prime is equal to K, I'm pulling out CA naught, so then I have 1 minus x to the 2/3. And I'm going to also pull out the 1 plus epsilon x, so this is over 1 plus epsilon x, and then I have, and I'm going to pull the 1/2 out of this, so then I have 1/2 to the 1/3 multiplied by 1 minus x to the 1/3, and this is multiplied by y RT. So then I can combine this 1 minus x. So RA prime is equal to K CA naught 1 minus x 1/2 to the 1/3 y RT over 1 plus epsilon x. So then I know that P A naught is equal to C A naught RT, so I can combine those. I'm just going to erase some stuff real quick. RA prime is equal to K PA naught 1/2 to the 1/3 1 minus x y over 1 plus epsilon x, and then I want to just combine these into a constant, and I'm going to call it K prime. So K prime is equal to K PA naught 1/2 to the 1/3. I know that PA naught is equal to P naught YA naught, and I can figure out what YA naught is from the stoichiometry. So I know that the I know that the feed is 80% inert, and then I know that I have twice as much A as I do B. So then I know that this is approximately 13.3% A and approximately 6.67% B. And YA naught is just 0.133, so P A naught is equal to P naught, which was 5, multiplied by 0.133. And then so I want to just solve for K prime. So K prime is equal to, and K is 30, multiplied by this PA naught, which was 5, multiplied by 0.133, multiplied by 1/2 to the 1/3. And that's equal to 15.87 moles per kilogram catalyst per hour. So now that we have the rate in a pretty usable form, we can plug that into the mole balance and solve it. So I'm going to erase some stuff real quick. FA naught dx dw is equal to and this is equal to the rate. So FA naught dx dw is equal to the rate. So we have K prime (1 minus x over 1 plus epsilon x) multiplied by y, so 1 minus alpha w to the 1/2. And I just want to be clear, if you were solving this problem and you set 1 plus x naught to 0 in this equation, then that would be correct too. That's fine, because it's telling you that it's really small, so it's practically 0. I'm just keeping this equation in a more general form for this, but I just wanted to be clear that either would be right. So anyway, then we can separate and integrate. So we have 0 to w, 1 minus alpha w to the 1/2 dw is equal to FA naught over K prime 0 to x 1 plus epsilon x over 1 minus x dx. So then if we integrate this, we end up with 2 over 3 alpha minus 2 multiplied by 1 minus alpha w to the 3/2 over 3 alpha. And that is equal to FA naught over K prime 1 plus epsilon natural log 1 over 1 minus x minus epsilon x. So then, just looking at this equation, we should have everything we need. We know what alpha is. We know x. So what we're interested in is when x is 0.2. We know what FA naught is. We know K prime. So we need epsilon. So if you remember, epsilon is equal to YA naught delta. Unless, of course, you just said that was 0, then your equation wouldn't have this, but just because mine does, then we know that YA naught is 0.133 multiplied by delta, which is 2 over 2, because A over A. no, this is, sorry, this is C over A. So 2, so C, yeah, so 2 over 2 minus B over A, so that's 1/2 minus 1. So that's equal to minus 0.0665. So then if you just plug everything in, so you plug in FA naught, which is 500, K prime, which we calculated, alpha, X, and epsilon, you get that W, for the weight of catalyst you need to get 20% conversion, is 7.41 kilogram. And I'm just going to do this again real quick for assuming that epsilon is 0. If you assume epsilon is 0, then this equation, you end up with this. So then this side is still the same when you integrate, so you get 2/3 alpha minus 1 minus alpha W to the 3/2 over 3 alpha is equal to FA naught K prime. This is the natural log 1 over 1 minus X. And even with this step, if you go back to the equation that I had derived earlier when I integrated this with the 1 plus epsilon x, if you just set the epsilon x to 0 in that equation, you also end up with this one. So then if you plug in alpha, FA naught, K prime, and X, then I'm going to do that real quick. So if you do that and solve for W, you get, calculating that real quick, I got that W is equal to 7.47 kilograms.